Great. Well, hello everyone. So yeah, my name is Laura Hayes, and I'm just going to build on what Daniel talked about and talk about how you can kind of access some of this data through the SunPy ecosystem. So this talk is really going to be a high-level talk about the SunPy project as a whole, and then some of the tools that you can use within the SunPy project for working with solar orbiter data. So there's not going to be a hands-on session part of this, but I'll link some notebooks. We're continuing to work to kind of make some more tools available through the SunPy project. And I think one thing just to remember is that the SunPy project is really a community-led effort. So if there's something that isn't available within SunPy that you would like to see there, please come and talk to us, whether that be giving feedback, whether it be contributing code or expertise. So this is, again, I'm giving this talk on behalf of the whole SunPy community. So there's some other main kind of contributors here. But again, I'm not representing all of SunPy. This is just me to promote some of the tools that are available. So just to begin, why do we need something like SunPy? Why do we need a software ecosystem for working with solar physics data? And where does Solar Orbiter fit into this? I guess we now live in really a golden age of heliophysics, right? We have remote sensing observations. So we have measurements at a distance, images of the sun with, instruments like EUI and Solar Orbiter or PHI. And then we also have in situ measurements, so measurements taken at spacecraft within the heliosphere. So example also from Solar Orbiter, we have 4 remote sensing instruments on board. We have in situ instruments on board. We have several in situ instruments on Parker Solar Probe and different instruments at Earth. So we have these 2 kind of different types of observations, and then within that we have a whole range of different types of data that comes down. We also have lots of ground-based observations, so things like DKIST. We have a whole suite of radio instruments and ground-based observatories. We now have these multi-messenger observatories such as Solar Orbiter and Parker Solar Probe, which add in kind of complications in some sense for analyzing that data when you go away from the Sun-Earth line. And then also we have data from a heliophysics perspective from planetary missions, so instruments like Bepi-Colombo or missions like Bepi-Colombo are taking in situ measurements of the solar wind and conditions in the heliosphere. And then as well as this, we have coordinated campaigns. So example, when Solar Orbiter is at perihelion, we have these campaigns where we're trying to look at the sun from 2 different viewpoints with a whole range of different instruments. And to do this and to take science from this, I guess you really need a way to get all this data in some format and for a user and a scientist to be able to work with it. And I guess in an ideal world, you would import some magical package. You would say, give me all of the data between these 2 times, analyze all this data for me and write me my paper. But we're really kind of far from this. And I guess, the last one is a bit of a joke, but I think the first 3 is really what we're kind of looking for. You want to be able to get all of this data from many different places in a very simplified way to do your science. And I guess this is kind of where the SunPy project comes in. And just to kind of give a definition of what it means, it's really a community of scientists and software developers that are trying to create that ecosystem I just spoke about, and to do it within the Python open source, openly developed community. So the SunPy project as a whole is really the people and the packages. And it's not just the SunPy package, which you may have heard of before, which is a Python package. It's also affiliated packages that build on top of SunPy that do specific things. So in terms of the project, if you think of it as a big umbrella, and on one hand, we have the code. So we have the core package, which I'll talk a bit about the different aspects of that. So this is, you pip install SunPy, you import SunPy. And then we also have affiliated packages. So this might be, something like, for example, we have StixPy, which is an affiliated package that works with the Stix data on board Solar Orbiter. We also have SunPy Soar, which builds on top of SunPy to access Solar Orbiter data. We have many, many affiliated packages, which I'll also go through. But again, it's not just the code, it's the people. So we have people like myself and some other people maybe on this call that are maintainers and contributors that are actually developing code and making sure that the project is keep going. We have community roles, people who are working with, hosting the website and, working with instrument teams and working with students. And then we, of course, have users. So if you use SunPy, you are part of the project. And one of the key things we really need is for the sustenance of the project is feedback. So I guess you are also part of the SunPy project. And then the wider solar physics community and heliophysics community is part of the project. So, we have community meetings, which are open. We run tutorials and workshops at summer schools and conferences. We're also kind of involved with the Google Summer of Code. We had some students this year that contributed to the project. Now, what I'm going to go through now is just the main core aspects of SunPy, the core package. And the 3 main components is data download. So going back to give me all the data between these two times, within SunPy, there's a thing called Fido, which is a unified querier and downloader for getting data, regardless of where it comes from, because we have data available from many, many different sources. So for example, from the Virtual Solar Observatory, you can get access to lots of data, the CDAL web, so lots of in situ data, from the JSOC if you're looking for AIA or HMI data. And the key thing is that it's extendable. So now we have it in such a way that we can access the Solar Orbiter archive, and you can build queries in the same way you would look for AIA data or many different types of data we can now do with Fido. The second main component is once you get your data, how do you contain your data? How do you read your data in? And within SunPy core, we have two main data types. So map, so this is remote sensing, an image of the sun with some coordinate system information, or we have time series, which is, flux or measurements as a function of time with some units and things like that. And then the final kind of core component, which is really maybe the most powerful and most important, really, now we're thinking of working with solar orbiter data away from the Sun-Earth line, is the coordinates package. So how do you look at a point in the sun from different viewpoints, and how do you relate them and do these kind of coordinate transformations? So these are the three main components within the core package. Now, of course, there is a thing extended out from the core package. So for example, SunRaster is an affiliated package to work with, slit spectrometer data. But these are the things within the core package, and just to remember. Now let's kind of go through each one individually. So for the data downloads, maybe some of you have seen this before or heard about it. It's a thing called Fido, which is again this unified API for searching or downloading data from a variety of sources. And the whole main key point is that a user doesn't need to know, which exact data source it needs to go and find that data. So this is an example. This is just from a notebook. We have lots of examples on our documentation. You import SunPy. And you can build a search by passing, different attributes, whether it be time, instrument, wavelength. This is just an example of looking for AIA data. And you just make this search, you get a result, and you can download it. And the key thing, again, is that it's extendable. So any new data source that comes available, we can write it in such a way that you can build a search in the exact same way as here. So for example, I'll show in a moment, you can change that instrument to EUI, and you can do the exact same workflow to get access to your data. Now, in terms of the different data types that we have time series. So this is, again, very measurements as a function of time. So we support many, many different types of solar-based instruments within the core package. But again, like Fido, this is extendable without the core package. And it supports different readers, so FITs, NetCDFs, CSV, and such a way that a user doesn't need to go and parse all those files individually. It can be read in this nice format. And again, it's a simple few lines of code. You import your time series, and then you can just pass your files to be able to make these type of plots. And again, it's extendable, so you can write packages outside of SunPy core, and this is done for solar orbiter packages such as StixPy and also Solo EPD Loader, which is a way to read the EPD data on solar orbiter. In terms of map observations, again, this is, as I mentioned, 2D images that have some coordinate information. And the key thing here is to be able to do the mapping between a pixel coordinate or array coordinate, and then where that is mapped onto the sky. And this is really important to be able to do any reprojections or to match observations together. So this is just, again, a nice example of AIA. And then, of course, it doesn't have to be a map of the sun. It can be a coronagraph image. So this is an example of mapping together EUI on board Solar Orbiter with SOHO LASCO in the same field of view. And you can see you can map. This was a nice large eruption that occurred in February 2022. Now, I think the most powerful thing, as I mentioned, is the coordinates package. And this is a really kind of crazy spaghetti diagram, but just to kind of highlight, I guess, how you can do these coordinate transformations between different frames, whether you're on a ground base looking up or you're in different kind of viewpoints around the sun and within different frames. And it's the sub-package within SunPy is a way for representing and transforming all those different coordinate frames. It's heavily dependent on AstroPy, which is another package which SunPy kind of builds on top of. And again, just to highlight, the blue ones are the ones within AstroPy, and then the see-through ones are basically the ones that are available through SunPy. And you can see these are all the helio-specific ones, whether it be helio-projective, helio-Cartesian, and things like this. And just to kind of show you how easy it is to use these coordinate package framework, this is an example of a helio-projective image in AIA, and this is in basically 3 lines of code. You can reproject that to a Carrington map. And that's really important if you're working in Carrington coordinates, or you're trying to do different things or compare solar orbiter with AIA at Earth-based observatories. And this is just to, again, to show this, if anybody's worked with Solar Orbiter already, or if you are in the future, you will be using this a lot to reproject the viewpoints between each other. And this is an example of an EUI image, so ultraviolet image from Solar Orbiter. And this is the orientation of the spacecraft with Earth. We can see it was at a 90-degree angles. And we wanted to see, what does this look like from the Earth point of view? We can easily reproject it to a different observer, which is really handy. And especially if you're trying to, like, for example, look at a region on the sun or an interesting flare or coronal mass ejection, you can reproject what would that look like from Earth. You can also do things like within LASCO, you can map, different catalogs of things in the sky. It allows you to do that coordinate transformations to heliocentric coordinates. And similarly, you can do fun things where, when solar orbiter is on the backside of the sun, like it was recently, you basically get a full sun view and you can make Carrington maps to see the 3D sun. And even further, you can use the affiliated package of SunKit PyVista to kind of get your 3D sun. So this is another example when solar orbiter was on the other side of the sun, we basically have this 3D view of the sun. And again, once you have your data within SunPy, you have the whole kind of ecosystem of Python to be able to play and do fun things like this. So this was a nice work that was done as part of the Google Summer Code, where a student kind of worked with some of our developers to extend PyVista to do solar transformations, which is quite nice. You can also do really nice things with comparing, thinking of multi-messenger observations in a very simplistic way from a user point of view. You can go from what would Solar Orbiter see and what did Parker Solar Probe see when there are two different viewpoints in the solar system. So this is an example at the Parker perihelion. Parker's very close into the sun and moving very quickly. And Solar Orbiter was out a bit further, and they both witnessed a very large coronal mass ejection. And in a nice way, you can use SunPy to use these two observations together to map what each one was seeing. So this is just, I guess, a nice use case again of things you can do within the SunPy ecosystem. Now, again, I've really only talked about the core packages, the core package functionality so far, but I've kind of demonstrated some of the other things you can do with the affiliated packages. So what are affiliated packages? They're basically well-maintained open source packages that build on top of the SunPy core that are a little bit specific to be in the SunPy core package. So for some examples of this is ND-Cube. So this is a way for working with n-dimensional data with a world coordinate system, which other packages are built upon. We have SunPy Source, so this is how we can access solar orbiter data through SunPy. We have SunKit Instruments and SunKit Image for doing, instrument-specific things or image processing with SunPy Maps. If you want to work with DKISS data, there's a DKISS Python affiliated package with AIA-Py, which is an affiliated package for working with AIA data. We have SunKit MagX for doing potential field extrapolations. And we have a whole range of them and a whole review process. So if you're working on an instrument, whether it be on Solar Orbiter or outside, you can of course become affiliated packages once it builds upon SunPy. And just an example of how this all works together. This is a plot, so this shows HMI, a synoptic magnetogram. This is AIA at Earth-based observing viewpoint. This is Solar Orbiter, which was at around 90 degrees, and Stereo A, which is again was away from the sunrise line. And using all the affiliated packages together, we use SunPy to get all the data. We use SunPy Soar to get the Solar Orbiter data. We use AIA-Py to prep the AIA data. Then we use SunKit MagX to get a potential field extrapolation from the HMI magnetogram, so it's a 3D potential field extrapolation. And then with the coordinate transformations, we can plot that from those three different viewpoints altogether. So it's just kind of a way to show how the ecosystem works together and how SunPy fits in to incorporate in solar orbiter observations. And if you're interested in learning more about kind of the ethos of the interoperable ecosystem, I recommend just having a look at our recent paper on this. And again, I can't show everything here, but on the SunPy documentation, there's a really nice example gallery of working with lots of different types of data. And if you click in these examples, it gives you the snippet of code, which you can download and run in a notebook or locally on your machine as a script. But where does Solar Orbiter fit into this? I've kind of highlighted some of the functionality that Solar Orbiter fits in and how we can easily, use what we've been working with other instruments for Solar Orbiter. Now, within SunPy already, it is, of course, not complete for working with every aspect of Solar Orbiter, but it provides a lot of the functionality that you already need to work with the data. And both within the core package of SunPy and now with affiliated packages, which are currently being developed and continuing to make progress to work with the data. So again, just thinking of the idea, the core package of SunPy, and then these are the affiliated packages that currently exist, which you can use to work with solar orbiter data. So these are SunPy affiliated packages. And I've added in here more to be added. This isn't by no means complete, but we're kind of getting progress, and this is where we need to work as a community to kind of build some more tools. Now, in terms of accessing data, you can basically access any of the solar orbiter data on the solar orbiter archive through SunPy, and I'll show some examples of that now. So you can download and you can query all of the data that you might need and get it through access through SunPy. Now, in terms of reading and processing the data, I've tried to list the different instruments here and what you can and can't do. Now, basically for all of the instruments, there is a way to read the data. Some of them is not complete for all of the data products yet, and that maybe needs some more work. But for most of the remote sensing instruments, you can read in this data using SunPy maps or a combination of SunPy and these affiliated packages. So the ones with the stars here are ones that aren't fully complete yet, but again, there are still ways to get it into the SunPy ecosystem. And I would really recommend, I think Daniel also linked this, but there are several other notebooks which show how to use these affiliated packages to work with these different data products to do kind of a scientific workflow. I'll link this again further on. Now, in terms of accessing the data, Daniel showed the Solar Orbiter archive. So of course you can go onto the website and you can search for your data there. It's the same way to get the data there or through SunPy, but you might want to access your data through kind of an API similar to way you would access other data. What SunPy Soar is different is that it hooks onto FIDO, so it's an affiliated package. You also need to import it. And then it allows you then to search for data that's specific to solar orbiter. So whether it be the instrument name, the detector name, the distance to the sun, which is something that's new about solar orbiter, usually we're at Earth. So for example, you might want to look at data that's only 0.5 AU in from the sun. And you can also look at things like soup names. So these are these campaigns that were run. So for example, in terms of the product, the different data products from the different instruments, you can list them all by printing solar.product, where you can also find that on the solar orbiter web pages. By distance, again, you can pass an attribute of distance to, you might only want to look at data close in or far out. And then, of course, by soup name. For example, if you're looking for all the data that's available with a nanoflare soup, you can also just pass this soup name attribute. What this might look like, again, thinking of a FIDO search, this is an example of just looking for EUI FSI images of a level 2 product. And we can just build that search in the exact same way you would search for AAA data or any other type of data that's available through SunPy. And this returns to you, information such as your start time or end time, your wavelength, and your soup name. So it's a really nice way to be able to access and play around with the data. And we're trying to work on the documentation for the Solar Orbiter SunPy Soar affiliated package. But again, you can go onto the website and have a look. We have an example gallery of ways you can kind of search for the data. And we need to add some more to this. So if there's something that you would like to see, please let us know, whether that be just tell us that you want this, or maybe you contribute. Or if something, of course, is not clear, we'd love to know. So an example here is just how you can look for EUI data within certain distances and things like this. And then once you have your data, there's many different types of ways you can load it in. Again, I would recommend going to the GitHub notebooks to have a look. But just examples of, once you have your file, you just, again, like within an ecosystem, you can just read this file in a nice way. So for example, just pass the file into a map, and then you can plot it within 2 lines of code. And similarly, that's with maps. Then you can go in time series. And this is an example of MAG, the instrument and solar orbiter. You can just read the data in as a time series, and it will plot it. It will know its units. It will understand how to plot, nanotesla and time and things like this. But again, check out the notebooks for more information on working with this data. Now, I just want to kind of finish it. How do you get in touch with SunPy, or how do you kind of become more involved with the community? All of the SunPy development is done in an open way on the GitHub. So if you want to have a look at the code, or you want to raise an issue, GitHub is the place to go, or of course contribute code. I think we also have an element chat, so there's always somebody online. It's similar to maybe a Slack if you're used to that, a different kind of variety of that. But there's always somebody online if you have any type of question, or you just want to come by and say hello, or I'm interested in working with SunPy, or I'm having this problem. There's no such thing as a silly question, so please come along and chat to us. We also have a discourse forum. So this is similar to a Stack Overflow type thing that we're trying to get people more involved in. So this can again be asking a question, showing something cool you did, whatever it may be. We also have a mailing list, which we're trying to phase out in kind of preference of the chat and the discourse forum. And of course, we also have a presence on the Helionauts webpage if people are involved there. We also have weekly developer calls on Wednesdays. If anybody would like to join, it's open to anybody. But for all of this information, just check out sunpy.org/help. All of this information is on the documentation. So I just want to kind of summarize everything here. It's kind of a quick, half an hour just to kind of give some introductions to this, but it's hopefully to point you in the direction of where you need to go and how you can use SunPy to work with solar orbiter observations. I think just the takeaway is the SunPy project is really like an umbrella, if you want to think about it, of the whole ecosystem, the people and the code, and it consists of both the core package and the affiliated packages for analyzing solar observations. I think with using SunPy within the Python ecosystem, there's already lots of functionality you need for finding and working with the solar orbiter observations. You can look and you can get access to all of the data. There might not be the tools yet available to do everything you might need to do. And of course, the majority of the tools so far are really focused on remote sensing, and that's just with the legacy of SunPy being more of a remote sensing package. But we would love to see more in situ functionality available within the future, maybe within an affiliated packages for solar orbiter specific instruments. Of course, as I mentioned, it's not complete. You can't do everything yet, but we are really getting there, and we would love your help to work together to have more tools available. And we're now starting a working group as part of the Mad Dog to kind of assess and coordinate efforts going on with writing tools for solar orbiter within the Python ecosystem. And then finally, we would love to hear from you. So if you're only getting started or you are stuck on something or anything, please come and talk to us at the SunPy chat. I think we are a community, and I think the community is key for kind of looking forward, and particularly for making the most use we possibly can from solar orbiter and working with the observations. So with that, I'll finish, and I'm happy to take some questions. And again, I just want to highlight, we're going to continue to add some more notebooks in this repository here. So you can see already there are different notebooks available. The most recent one is the one from the Solar Orbiter Eclipse meeting in April of last year. So thanks very much. Happy to take some questions.